get started then. I am getting myself into Teams, I'm getting us into our notes, and I'm turning on the projector. Maybe. So last week, we started talking about valid and invalid arguments. And we talked about modus ponens. We did talk about modus ponens? We did page 10?
Yes.
Weird. You have it filled out too?
Yep.
That's good. So modus ponens is when you say P implies you have two premises and then your conclusion, but one of the premises is a conditional. The next one is the first part of the conditional, and the conclusion is the second part. That makes sense. Logically, you can see why that would work. Why is this not turning on? I should be able to press it from here. There we go. We have live. Okay, and then we did show with a truth table. Oh, we were talking about critical rows. That's what we were doing. That's how I sort of ended class. And then I shooed you out of here after time. And Brian had been packed up for like 5 minutes at that point. I know, you're fine. I went over. That's on me. You can do whatever you want at 12:20 in a second or something. Okay, so let's talk through that again before we move on to page 11. So, an argument, the form of the argument, you do premise 1 and premise 2 and however many premises there are until the conclusion. Implies the conclusion. So this is what we call this the logical statement of the argument. It's just the symbolic argument. So when we have something like this one, the modus ponens form here, premise 1 is this, premise 2 is this, and this is our conclusion. So premise 1 and premise 2 together should imply the conclusion. That's the statement. That in itself, I don't think it's that hard to get. Doing a truth table for that, you're going to do this truth table for this conditional and make sure that you get a tautology, right? The thing about the critical row is that this thing, the hypothesis of the conditional statement, right? If it's false, what happens? Let's talk through that again without me just shouting at you. So if we have P implies Q, oh my, what does this truth table look like? We have true, true, false, false, true, false, true, false. What do we have over here? True, false, true, true. Notice how when the first part is false, this thing is going to be true every time, regardless of what's happening here. Okay, so that means in these 3 rows, it's true, and that's free, right? So it's irrelevant. What does matter is that we get a true in this row, where we won't necessarily get it for free because this part is true. We have to know that the truth of the conclusion follows the truth of the premises. Yeah? So that basically this means you can fill out an entire truth table for this, make sure you get a tautology. Or most of us are looking for shortcuts in our lives, right? Yeah, here is one. I don't have to do the whole truth table. I need to look at the critical rows and make sure the truth of the conclusion follows the truth of the premises. So the place where my premises are true is here, right? And I need to make sure the truth of the conclusion follows. And it does. So the fact that I get a true here, or the fact that this is true, does work. This thing is a valid argument then. Does that make sense to you, the critical row sort of argument there? It saves you a lot of time if it's a whole bunch of rows. Here, it doesn't take that much time, but if it's a bigger statement, it would save you significant time. Or your computer program, lots of space. Emily, what's up?
So can there be multiple critical
Yep.
rows?
Yep. That's a great question. My examples have changed, and now I don't have an example in the notes that has more than one, but yes. Okay. So this is valid. And we are ready to look at some rules of inference. This is another one of those things like the common logical equivalences that is like good to be able to refer back to, like maybe put these on a note card to use them. So you have these arguments here. It's basically what's inferred by these premises. This is the rules here. So that first one, it's in the wrong order, but that's modus ponens. Yeah. So what is implied in that first one? Q. Yeah. So this is modus ponens. I need you to know that I got a PhD in math and never heard the words modus ponens until I started teaching this class. So is that me? It's you. That's fine. I'm not bothered by it at all. That sounded sarcastic, Sharad. It was not. This is the problem with being sarcastic all the time, is that it is unclear when I'm not being sarcastic. Okay, this next one, what do you think? It is not P, but why?
So it would negate with the Q, but then it can't associate with it.
This is because it's the contrapositive, right? Remember, P implies Q is equivalent to not Q implies not P. Y'all don't remember this because it's been a long time since I've seen you, but that's the contrapositive. And remember, the converse of a conditional is backwards. So the converse is Q implies P. The inverse is the right order, but negating the pieces, so not P implies not Q. But these two are the ones that, those are equivalent with each other, but the contrapositive is equivalent to the conditional, and so you have, like, this is called modus tollens. Again, PhD in math, never heard of it till I taught it, so. But anyway, that's modus tollens. So modus ponens is just the conditional, modus tollens is the contrapositive. This is going to be useful for us when we're doing proofs, because you can, when we're doing proofs, and this is 4.1, it's coming soon, but we're going to like assume P and show that Q follows, and that's called a direct proof, or you can prove indirectly, which means you suppose, not Q and show not P, right? The fact that they're equivalent means you can work with either one of them. Okay, so modus ponens, modus tollens. How about this one? Yeah. The Q part sort of gets squished out of there. This is the transitive property. How about the next one? We have P or Q and not P. I'm telling you it's P or Q, and also it's not P, so it's Q. Yeah, good. That has a name, but I didn't write it down, which is unhelpful. This one, this next one, we're not going to guess because I don't know how you would, but this is generalization. If it's P, then it can be P or anything else. This one is specialization. If it's P and Q, then you can conclude it's just P also, or it's just Q, either one. Bonus points in my heart for whoever gets the next one. It's P and Q. Therefore, it's P and Q. Okay, this one is good. I like this one. P or Q, and also not P or R. Q or R. Okay. So we are going to use our truth tables to talk about these two things and whether these argument forms are valid or not. So you can see, hopefully you can see that one is the modus tollens form. You see that? This is P implies Q and also not Q, so not P. That's this guy. We're going to prove that with the truth table. This one we'll also show in a second, but let's do the first one. So P, Q, P implies Q, not Q. Now, how do you want to do this? Do y'all want to do the whole truth table? You want to do critical rows? Emily, I don't know what you said. I heard you speak, but I don't know what you said. Oh, you didn't say anything? Mm. Michael.
Is there a way we can figure out the critical rows?
Yeah. You want to figure out what they are?
Is that by doing a truth table?
Yeah. Yes. I guess my thing is like, I don't know if you got the critical row thing or not. So, okay, let's just do the whole thing and then we'll talk about what's the critical rows. I'm going to label these 1 and 2 for our premises here. So 1 and 2, we'll call this 3. Gosh, I'm going to run out of space. Okay, so I do my first 2 columns just like normal. I'm going to do P implies Q. I'm going to do not Q. Okay, so those are the 2 premises. So I'm going to combine them now with an and statement or conjunction. So I'm looking at this, which means I only have a true down here. The rest of these are false. What does that actually tell me?
Critical row at the bottom.
Yeah, the bottom's my critical row. So I don't have to do anything else. I can look at what not P is there. So what is not P there? It's true. So that means this argument is valid. But let's suppose we don't know the critical row argument and we're just going to fill in the whole truth table and look for tautology. Good? But that's enough because the truth of the conclusion follows the truth of the premises. The one row, there could be more than one, but the one row here where the premises are all true, the conclusion is also true. Right. It's just the premises themselves. So this is premise 1 and this is premise 2. So you're looking at specifically those 2 columns or however many there are. There could be many more premises. Premises. I like that better. Yes. Okay, so let's suppose that we don't know the critical row argument, so we're just going to fill in our truth table. We're going to go with not P, so F, T, T. And then we're looking at 3 implies that, so false implies, okay, true, 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 true. And my argument about the critical row thing is that these 3 are free, because of these three falses. False implies anything is true. So the conclusion's truth or falseness doesn't actually matter. So, but this is a tautology, so it is valid, or you can say it's, you know, the critical rows, the conclusion's true in the critical rows, so we're good to go. Do you have any questions about that, or does that make sense? We are good or not good? We're good. Oh, you should actually answer the question. This is valid. You're pretty early. Yeah. Like, right? Aren't you an hour early for class? Aren't you?
Oh my god.
Do you want to be here for this class? Okay, well, then go get lunch or something. I'll see you in a little bit. Okay. Okay, I should have just let her sit there. Okay, this one, we have P implies Q, also Q, all of that implies P. So the like logical statement here of the argument, this is P implies Q, that's premise 1. Premise 2 is just Q. All of these imply P. Okay, so we have P, Q, P implies Q. One and two. And then 3 implies P. Should I have let you guys tell me all the columns? Or do you got this now? You got this now. I hate when I ask or questions and then have no idea what your answers mean. So I appreciate you answering with words instead of just nodding. No. Yes. I'm sorry. I'll try to ask better questions. All right, true, true, false, false, true, false, true, false for P and Q. P implies Q. We have true, false, true, true. 1 and 2, we have true, false, true, false. What does this mean? And. Yeah, first and third are critical rows. And then we want to look at the truth of the conclusion in those rows. So our conclusion is P, right? Here it's fine. There it is not fine. So this is not a valid argument. Yes or no? Does the critical row thing make sense? You want me to keep going? Let's do the whole truth table. We'll see that we don't get a tautology here. So this one we're doing, this implies this. So true, true, false, true. So you can see that this is an issue if you're doing the whole thing because you don't get a tautology. Good? Okay. So right below this, we're going to be looking at 3 different arguments, and we're going to talk about which of these rules this uses. Okay? So number 3, we have it's below freezing now. Therefore, it is either below freezing or raining now. So I'm going to assign some variables here. So it is below freezing now. Therefore, it is either below freezing or raining now. This is the generalization. Good. It is below freezing and raining now. Therefore, it is below freezing now. Specialization. You know how impressive it is that we can read? It's pretty impressive. Like, and that we don't even notice when somebody does something like this and all the letters are all connected. I'm not writing in cursive. I'm just lazy. Right? Like those are not what all those cursive letters look like. The Z is the only one. Why is Z different? I don't know. But like my kid, is learning to read, right? And could he do that? I don't know. Like at what point does it just become so second nature to us that we can? That we don't even have to think about it.
Have you ever seen those like Instagram reels where they have like a paragraph where like it would say for instance
Oh, the words are all jumbled and we fix them. Yeah. You read that wrong. You also read that wrong. You read that wrong. Like what? Did I?
Read that again.
Yeah. Like, oh, our brains are so fascinating. And to me that's like, yeah, God has to exist and has to have designed us, because how else could we possibly, like, the believing that all of this happened by chance to me is so much crazier than that somebody created it. But anyway, that is just, it's so wild to me. We don't think about it. We don't think about the fact that I've connected all of those letters. And like that these don't even look like letters anymore. Like it's just, it's just there.
It's the only way people can read my handwriting.
But like I'll write stuff and my son will be like, or how weird the English language is, Like, have you guys seen the person on Instagram that's like, how do you pronounce this word?
Oh,
Yeah. Okay. So,
beer.
right. No, it's like like, why? Because it's a bunch of different languages combined together. I get it. But like, also, here's another thing. Here's the thing that blows my mind. Sorry, this is a distraction, but you need to talk about it. I wonder, I don't think that we all perceive color the same way. Obviously, there are people who are colorblind, but are color, I don't know, deficient. But like, I think that we're told, like, this is white. And that we may see white differently, but we identify, like, this thing that we've been told is white is white. Does that make sense? But like, maybe what I see is pink, Sharad sees as white. Does that make sense?
So like we all have the same favorite color.
Yes! Emily, what if we do? If it's like whatever our eyes are letting in. And we all have the same favorite color. I call it red, you call it blue. That has actually blown my mind. Do you think that we do?
I'm not sure. I actually took a class where we perceive blue and green better. Obviously, we might think it's a different color, each of us.
Right.
It's because of like the green and blue around us. So I asked a really unethical question that he couldn't answer because I was like, what if we took babies and put them in a simulation where they made the sky red and the grass, I don't know, blue? Would they perceive red and blue better?
Yeah.
And he was like, I don't know. But it's so unethical. I don't think we can do that.
No, they would not let you do that.
Chemicals can make the sky red.
Do y'all have those moments in your life, speaking about greens, do you have those moments in your life where you're like, that like really put you in your place and like, God is really a big God? For me, that moment is when it is sunny, but like raining, because like the sky is gray, but the greens are so green because of the gray sky, and you can see all the different colors of like green leaves on trees. Like, that is for nothing but our enjoyment, right? I mean, maybe God's too, but like he made the trees all different colors of green for us. Well, think about how many trees there are. Why? Next time we have an afternoon storm, which we do, every day, go outside. The sky will be gray, and up against the gray sky, you will see these like bright green trees. I'll find a picture and show it to you. Okay, if it rains today, well, what I perceive to be green, maybe you know whatever. If it rains today, then we will not have a barbecue today. This is weird. If it rains today, then we will not have a barbecue today. If we do not have a barbecue today, then we will have a barbecue tomorrow. Therefore, if it rains today, we will have a barbecue tomorrow. This is the transitive property. Y'all don't even need me to write down the letters? Okay. If it rains today, then we will not have a barbecue. If we do not have a barbecue today, then we will have a barbecue tomorrow. Therefore, if it rains today, then we will have a barbecue tomorrow.
It's like bonus color square.
Sure. Okay, we good? Feeling good? Okay, let's keep going. So you might have gotten to the point of realizing that an argument like this would be super annoying to do with a truth table. And we don't have to. We can use those rules of inference one piece at a time to get to this finished puzzle. And this is fun. However, it's hard to organize. I'm going to do it the way that makes sense to me. Your textbook will like renumber things, and I find that to be really confusing. But I'll show you how I organize my thoughts here. So what we're going to do is we're going to write down our premises in a like vertical line. That's what I'm going to do. So I have not P. I have P implies Q. I'm trying to get to this conclusion Q. This one's not hard. So we're going to go one step at a time, try to combine things or do some things to get to where we can say, okay, Q follows from like using these guys. Okay. So not P, we're going to just rewrite as P. Careful with arrows here because you'll notice that's why mine is a line, because a bunch of arrows are going to get very confusing unless you're using a different kind of color for your arrows. What does that mean?
You know, like when you need to write your name in like balloon letters.
Oh, like this. You just, I can't look at that. Not like that. Pass.
Like this.
Oh, in the shape of an arrow. Dr. Thomas, could you maybe do it in the shape of an arrow? Okay. And then I hope that you can see this, maybe that we can combine these two and we get Q. And I'm going to go through and write this. This is negation. That gets us to there. This is modus ponens here. So we get our conclusion Q. That one's relatively straightforward. We can do harder ones, though. Are you ready to try? Okay, I'm going to write down the things I have. Not P implies Q. All these parentheses are messy. Not R implies not P. Not Q. R implies S. And we're trying to get to S. God, it's so quiet without that. I'm ready. Go for it.
So I know that the not P and the Q and the not Q, that would be the modus tollens.
Yeah.
So that would just become not
It would become not P.
P, right? And then not P.
Is P. Yeah. So combining these two, maybe I should move up here. Combining these two, we're looking at not P implies Q and also not Q. So that is going to be not P. That is modus tollens. So not P. Huh? What did you say, Janai?
Not P.
Yeah, because so modus tollens actually has this, right? Yes, it would just be P. That's just, you're doing it 2 steps at once.
Oh,
And then not P. P cancels out with not P from not R. If not R, then P. Not P. Like speaking of gibberish.
I didn't understand it, so maybe you are. What?
So it becomes P.
It does.
P then cancels with not P from if not R, then not P.
It doesn't cancel. I don't like that terminology. We're going to use it with the other thing and do modus tollens again, right? See how this could get messy organizationally? So we have, on this one, we have not R implies not P. Oh, it would help if I wrote down the letters correctly. Oof. Not R implies not P. And then we have P, so we should get not R there. With also modus tollens. So that is R.
Modus ponus.
Yes.
So the R's go away. And then you're just like this.
Does that make sense? You got it too, though. That's good. Yes.
I was about to ask, could we just do the transitive where it's not R implies not P implies Q?
Yeah, not R implies Q, then use modus tollens there. Uh-huh. Yeah. Yeah, you could do transitive here, so not R implies Q. And then that with this and modus tollens gives you R, or not R, R, and then R implies S gives yes. Mm-hmm. Either way. No, you may not. It's a puzzle. Okay. You can pick one of those two to do with me. Which one you want to do? 3 or 4? Let's see if 4 is harder.
Because you're getting to a conclusion that's not just
Okay. Nice. Let's do it. 4. Do you know that I have a student whose name is Jemiah this semester? So every time that I speak to you, I'm like, which one is it?
If it makes it easier, you can just call me Naya.
It does. But I've been calling you Janiah for years. So it feels weird to change now.
It's a little late to try to rebrand.
You may not rebrand. Don't try. This one is, Janiah, you're going to do this one because it's not actually hard and you can. But that sounded awful. I'm sad that I'm recording myself. That didn't mean that the way it sounded at all. I was trying to build your confidence, not stomp on it. It's built. So. Okay, maybe it is hard. I shouldn't have said that.
I don't even know what was
We're trying to get to this thing. Yeah, that is hard. We're trying to get to this thing. So like, and like I can see that I can combine these maybe. Combine those second two with the transitive property.
Oh,
That's what you guys are doing.
I was wondering, like, I don't know where you guys were pulling all this stuff.
That would be a great time to ask that question. Okay, what should we do now? If I have not P implies S, then using the transitive property. I was even labeling them. We can. I wouldn't steer us that wrong. I mean, hopefully. This is a way to do it.
Would you be able to do the contrapositive?
Sorry, that was a dramatic reaction. I apologize. My children doing that when I'm driving the car, like, ah! That's not good for anyone. Okay, Eunice later is going to watch this video and be like, what was she doing? Good? Questions, comments? What do you think? We can do this, right?
Oh, I see. I get that.
That's good, right?
Because then those not P's would cancel each other out.
Yeah, I hate that y'all are using that terminology, but yes.
Or like, what's the term, like?
The transitive property.
Oh, the trans.
Yeah. I would like to say that they get sort of squished out, right? They're still there. They're just like hiding in the others. Yeah? They're not gone. Maybe. Okay. Going on to section 3.1. We can do a lot of things and we're doing really good. Is the sentence x plus y is greater than 0 a statement? Remember, a statement is something that is either true or false. Not yet is the answer. Oh, see, like there. These aren't real letters, but they look pretty. That says because we don't know anything about x and y. So that statement can't be true or false. That thing is not a statement, so don't call it one. That thing is not true or false, and so it's not a statement yet. So a predicate or an open sentence is a verb phrase that describes a property of objects or a relationship between objects representative of variables, like that thing we just did. That could be an open sentence involving x and y. But what happens is that you are given like numbers so that you can decide if it's true or false. So let's look at this one without two variables, just one thing going on. So we have x is greater than 3, x is a subject. You didn't know this was English, but x is a subject, greater than 3 is the predicate. This refers to the property that x can have. So p of x here is that x is greater than 3. Once the value is assigned to x, p of x does become a statement and has a truth value. So what does p of 2 mean? This is a lot of words, but p of 2 means that 2 is greater than 3. Which is false, right? So now it has a truth value. What does p of 4 mean? And that is true. Whoa. Those are not letters at all. Sometimes it can involve more than one subject. You have here Q of x, y. It's the relationship that x is equal to y plus 3. So this is defining a relationship between x and y. What does Q of 1, 2 mean?
Equals 2 plus 3.
Yeah, which is false. What about Q of 4, 1? And that is true. Doing okay with what a predicate is? Okay. Next up, we are going to talk about quantifiers. So this is, the title of this section is Predicates and Quantified Statements. So what is a quantified statement? We're going to talk about that right now. So the phrase, there are two quantifiers in math that we use a lot. One of them is a universal quantifier. That is for every. Red is aggressive. This the universal quantifier is for every, and that is an upside down A for all. Yeah. The other one is a there exists. That's the existential quantifier because it exists. It's saying that one of them exists symbolically. That's a backwards E. Because an upside down E would just be an E. So I got to make it backwards. Okay. Okay, so for all, that means for every. There exists, that means there is at least one. Yeah? We good? What we're going to do right now is decide if these are true. And then we'll move on. So for all x and r, do you know what that big R is? That's the real numbers. This is a blackboard bolded R. That's the real numbers. So for all real numbers x squared minus 4 equals 0. That is not true. Good. That is false. How do you know that that's false? Good. Next step number 2, we have there exists an x in the real number. So there exists a real number x such that x squared minus 4 does equal 0. This is true. How do we know?
Find out which thing it is.
Which thing is it? Or which things? Yeah. Okay. So you can see the symbols here. So symbolically, statement 1 is like this. For all x in R, x squared minus 4 equals 0. And then the second one is there exists an x in R where x squared minus 4 equals 0. Tracking that, the symbols? Yes? Okay. I think we'll have much more time to practice with that in a moment. Oh, yeah. That's what page 15 is. We're going to do just fine. Okay, let's keep going. We have we don't have to include a symbol for such that, I kept saying it, but it just follows from the stuff. So there's no symbol. In set notation, we use a bar for such that. Do you know this? This is fun to teach you guys. The set of all x such that. That's what that means. Such that, I don't know, -3 is less than x, which is less than or equal to 2 or something. Right, that's a such that. Just kind of fun. A little piece of math knowledge for you. Never thought you wanted or needed. Okay, so we don't have to do that here. We don't have to have a symbol for that. It follows the first there exists, just so we know. Follows the first there exists. because there could be lots of things going on. Okay, there exists can be interpreted generously, where it includes a situation where there's only one X that fits, or there are many X that fit. For it to be true, there needs to be at least one. In some contexts, I put your paper right there for you. You can sit wherever you want, Eunice, but no, it's yours. In some contexts, we decided all of our variables will be taken to be coming from some fixed universe of discourse or domain. That is a lot of words. You got to define the domain. That's what that means. So we're going to do this, and we're going to be creative. I have an example that's not creative at all, but maybe you guys can help me come up with a creative example. So we want to provide an example of the predicate P of X where the statement for all X, P of X is true.
X is equal to X.
You can choose what you want. If you don't have to even use numbers, you could use like people. So for all X in R, wow, that R was going to have 3 things. For all X in R, X times 0 equals 0. Good. I had that X squared was greater than or equal to 0. I think yours is more creative, so we'll go with that. Okay, so now we want to provide an example of the predicate Q of X where the statement for all X, Q of X is false, but the there exists statement is true.
So X squared equals 16.
Sure we can. Not very creative, Brian, but that's fine.
It didn't specify the need for creativity.
So for all X in R, X squared is equal to 16. Is that what you said? So this is false. But if we do, there exists an X in R such that X squared equals 16, this part is true when X is 4 or negative 4. Or is true because X can equal 4. Okay, so this is important. This is what 4.1 is. So this is sort of jumbled a little bit, but a counterexample is a specific example that makes a for all statement false. So if I said like for all people in this room, S of P, S is that P grew up in South Carolina. What would we need to know to prove that this whole thing is false? I say for all students in this room, all people in this room, sorry, the people grew up in South Carolina.
Someone didn't.
Yeah, that someone didn't, right? Me. Eunice. I don't know. You. Whoever else, right? It's enough to say that just one of us didn't. Our counterexample here to prove this false, let's go with me. I grew up in Tennessee. Okay, are we good so far? Yes? Yes, doing great. What I said earlier about the such that goes right after the first there exists, that's important. If you don't do that, it changes the meaning of statements, and that's confusing for everyone. So, but also the order that they're in can change whether the statement is true or not true. So let's look at these examples. um, so we have m of xy is the predicate that x is married to y. And so we want to discuss what these symbols mean. Number one, we have for all x, there exists a y such that x is married to y. I'm going to write that down. We're going to write that down. So for all x, there exists a y such that x is married to y. What is a way to say that in a less convoluted way?
All X's are married, so X
Yeah.
equals Y.
They join as one, yes.
XY.
But it would be better to say something like what Brian did, that everyone's married to someone. The X pairs up with Y. Yeah. So that's how I'm going to say it. Everyone's married to someone. Okay, number two is that there exists a Y such that, remember, because the such that goes right after the first there exists a Y such that for all X, X is married to Y.
So as long as there's an X.
It is weird.
Y is just married to everyone.
Correct. That is what I'm saying. That there is a person, Y, who is married to everyone. That is alarming and a problematic for everyone involved. So the order of those quantifiers matters. This is the point, right? This says that there is someone who is married to everyone. Look at the face I drew in my own notes. This is the face of alarm. Oh, okay. Number three, there exists an X such that there exists a Y where X is married to Y. Yeah. There was someone married to someone.
But it's all in all.
All the people are married to all of the people? Yes. Everyone's married to everyone. And it's pure chaos. And everyone is dead then. Right. And then we're,
Just two people.
maybe so. If we don't have any domain defined here, and that's bad. This is bad practice. So if it's just two people, then maybe we're okay.
I guess that it would.
In a general sense, what area is all.
You can, that's fine. Yep, they all match up with everybody or whatever yeah, that's fine. Okay. We get to practice. If you thought, ooh, I'm not really sure about all of that, that's fine. We're gonna practice a bunch and you're gonna be sure. So we're gonna put these all in symbols and talk about them being true or not true. I know you guys have an error on your paper. I have fixed it since but because I saw it when I was prepping. These should have R's there. This is a coding problem that I code differently than whatever I copied, and so it didn't transfer well. Okay, so we're gonna put these in symbols, and then we're gonna talk about whether or not it's true. Number one, there exists a real number x, so there exists an x and r. We haven't talked about that symbol either. Do y'all know what that symbol means? Well, it's an epsilon. Oof. This guy is an element of, these are the real numbers. This is our there exist. A little e is the little epsilon is a element of, so it's a set notation thing. Like 2 is an element of 1, 2, 4, 5. You get what I'm saying? Okay. So there exists. Why didn't anybody ask me that? Oh, because it wasn't back here. That's why maybe. I did it there. I did it there. I did it there. Y'all just went with it. Nobody asked. It's an it's an element of the real numbers. It is part of the real numbers. That's why it's there. Okay. Not part of the R, because it could be anything there, any set. That's just a set of real numbers. Okay. I don't know what we're doing. Number one, there exists a real number x such that x squared plus 1 is greater than 0. True or not true? How do you know? Good. Okay. Number 2, if x is a real number, then x squared is a real number. Write this with a quantifier. How do you do that? What's the quantifier? There are 2 you can choose from. There exists or for all. What's the way to say this with a for all statement? Darn it. What's the way to say this with a quantifier? For all. For all x in R, and then do it. If x, oh well, for all x in R, oh gosh, x squared is in R. True? False? Do we know? Can we prove it? Not yet. Okie dokie. Number 3. X cubed equals 8 for some real number x. Put this as a quantified statement for me. Yeah, there exists an x in R such that what? X cubed equals 8. True or not true? How do you know? Okay. This one's tricky. What's the quantifier on number 4? Yep. For all x in R, what do we know? x squared is greater than 0. What are we saying? True, false.
False.
How do you know? What is this thing called? Good. Yeah. Counterexample. That's how you prove a for all statement to be false. We'll get there. We're doing it now, and we're going to continue doing it. It's good to see. The square of an integer is a whole number. You can use W for whole numbers. I'll start you out. For all x in integers is z's, y'all. A blackboard bolded z.
So would it be the square of x exists in W?
I don't know how to make that W. Yes. For all x in z, so for every integer, when you square it, you get a whole number. Whole numbers are non-negative integers. So 0, 1, 2, 3, 4, 5, yes. Okay. Number 6, there is a natural number n such that n squared equals 36. There exists a natural number. The natural numbers this is called a blackboard bolded n for the natural numbers. That's 1, 2, 3, 4, 5, so on. What you would naturally teach a child to count. You wouldn't start at 0 unless you're some sort of monster, or -2. You would start at 1, which is where the natural numbers start. Okay, there exists an n and n, so there exists a natural number such that n squared is 36. True. Good, when n equals 6. Okay, let's keep going. For at least one real number x, x squared minus 3 equals 0. There exists a real number x. So there exists an x in R such that x squared minus 3 equals 0. I believe that this is false also, because x would have to equal, oh no, that's a real number, right? The square root of 3 is a real number. So this is true.
I didn't know for sure.
Yeah, it's irrational, and then later we'll prove that, but it is still real. This is true. Whoa, whoa, whoa. Those letters are not, that's fine. X is going to be plus or minus the square root of 3. Either one is still real, so that's fine. Any real number is also a complex number. This would be for all x in R. X is also in C for the complex numbers. This is true. Okay, what do you think? We're doing okay? Emily, you doing okay? You wanting to know what the complex numbers are?
Well, I'm confused, like, what's the Z and 5?
The integers. Yeah, I did do a bunch of things here. This is the integers. This is the whole numbers. This is natural numbers. This is complex numbers. I don't know, like, at what point you're supposed to learn that sort of thing. You know, like where that falls in the curriculum.
Discrete.
Apparently. Yes, now. Okay. Yeah. Good. We good? Okay. let's pick 3 of these to do. We shall pick 4, because Shania's going to pick 4. And 3. Okay. And we can pick 1 more. What do you want? Okay. Somebody, if you want to be so brave. No, I'll do it. There exists an n in the natural numbers such that all numbers bigger than it, for all numbers bigger than it, 1 over n is less than 0.01. That is quite a statement to be making. Okay, so can you come up with an n that would go here where, no. Can you come up with an n that any number bigger than it we could put there and make this true?
Yes.
Fine, yeah. I used 100, but 1,000 will work too. 100 what? Does that make sense? There exists an n such that for all n bigger than, yeah. Because if n equals 100 or 1,000, then for all n bigger than 100, 1 over n would be smaller than 1 over 100, which is equal to 0.01. Woo, that's tricky. This is true. That's what we're supposed to be doing, deciding if they're true or false. Number 4, that's the integers again. So for all integers m and n, if they are both even, then their sum is even. This is true, and we're going to prove it later. Like maybe next week. Okay, number 5, for all natural numbers x, there exists a natural number y such that x minus 2y equals 0. It is false. Why?
X is 1, and you have to have 1/2.
Yeah. This is false. If we choose x to be 1, so then y would need to equal 1/2, which is not in the natural numbers. If this said real numbers or even rational numbers, we would be fine. Okay, when we do stuff like this, you guys, now I did not do a good job of this in the married example, but stating what the domain is important. So go ahead and actually do that. And then these 2 things, the last 2 things we're going to do today, we've done so well, y'all. So the last 2 things we have this, like, we're going to talk about negating quantifiers here in 3.2 and 3, but we'll do that soon. But the first thing is that I want to ask you is, are these quantified? So read this. If a number is an integer, then it's a rational number. And the second one is the number 24 can be written as the sum of 2 even integers. They don't read like they're quantified statements, right? But they are. This is called implicit quantification because it's implied. The way that you could rewrite this is for all integers, or for all x and z maybe. X is a rational number, that's a q. Let's throw some more letters at you. These are the rationals. I should have done a bubble diagram. That would have been easier. The next one, the number 24 can be written as the sum of 2 even integers. I'm gonna throw another one at you. So there exist x and y in 2z. That's your even numbers, even integers, such that x plus y equals 24. Why is that 2z? We'll talk about it next time. Hi, Justin. That's all that we have for today. And we did it. I said 5 pages and we did it. Eunice, things were really strange for a while at the beginning of class, so I look forward to hearing what your reaction is in the video. Oh, what does it say on Blackboard that it's through? What's the last question on that homework? Okay, it looks like probably you can do half of these. So the negations of quantifiers we haven't talked about yet, so you would want to skip some of them. So probably next Friday. Sound good? All righty. Yes.
So like the question one was to determine that the following argument is valid.
Mhm.
Can we do either truth tables or the?
Yep. Yep. I don't care which one. That one, I don't know which one's easier, but like this one, you obviously probably wouldn't want to do a truth table for. Yeah. Yeah. I prefer the actual.